So now we want to maximize this function, f of xy equals x squared plus 3y squared, along the curve x squared plus y squared equals 1. Now I didn't use the word constraint in class because I didn't want to do a whole lot of stuff that would distract people from the main thrust here, but this is called our constraint. And this is called our constraint. So when your book starts using a big word like constraint and you don't know what the heck it means, well, hopefully you've seen this. And you know it's just that function that describes your curve, okay? Now there's more to it than that. You generalize to higher dimensions and stuff. But if you understand it here, it's fairly easy to generalize, okay? Well, this function is just a function we've used quite a bit. It's just an elliptical paraboloid, narrower in the y direction than in the x direction. But it's nice and parabolic in all planes through the origin, and just about any other vertical plane. And this is your constraint. Well, this just means that, okay, we're going to maximize this, the values of this, around the unit circle, the circle of radius 1 to about the origin, which is clearly this, and we know this. Okay? So we're going to use this method, so we immediately just jump, okay, let's do del F equals lambda del G and see what comes out of it. Okay, well here's del F, here's del G. And you can do that. It's simple enough that I probably even did it right. Okay? Now, to say del F is lambda del G, well, we just put this on one side, put this on the other side in parentheses, and put lambda in front, right? And then this, of course, the I components have to be equal and the J components have to be equal. So we get two equations out of this. Okay? Now, there are actually three things we need to solve for. That would be x, y, and lambda. And ordinarily, we have to do something that you'll see in the next example. But for this one, we actually have enough to figure it out with just the two equations. Because 2x equals 2 lambda x, that's going to happen only if lambda equals 1, right? You could obviously solve for lambda, you're going to get 1. Okay? And then 6y has to equal 2 lambda y, but lambda equals 1. That means 6y has to equal 2y. Well, that can happen. What's the value of y? 0. So, if y is 0 and lambda is 1, you get the coordinates of a point and the value of lambda. Well, I'm going to say 2x equals 2 lambda x is okay if lambda equals 1, as long as y equals 0. Okay? Now, what are your coordinates of x and y? X could be any coordinate at all, except your point has to be on this curve. So y is 0 and you're on this curve. That means that x, well, it means that x squared has to be 1, so x is plus or minus 1. Okay? So if y is 0 on the curve x squared plus y squared equals 1, then x is plus or minus 1, so that your points are 1, 0, and negative 1, 0. And at these points, this condition holds, with lambda equal 1. So at these points, del F is equal to del G. Okay, now, you have another solution. I mean, if lambda equals 3, then this equation holds, whatever the value of y. So if y has a non-zero value and lambda equals 3, well, I mean, we don't even have to have y having a non-zero value. If lambda is 3, then what does this equation tell you? Well, it tells you 2x equals 6x. That only happens if x equals 0. So we get the point 0, y. Okay? I didn't write it down here, but that, on the curve x squared plus y squared equals 1, if x equals 0, y has to be plus or minus 1. So we get the point 0, 1, 0, negative 1. Okay? So, what we have here is what you get when lambda equals 1. Okay? If lambda equals 1, y has to be 0, because otherwise this equation won't hold. And if lambda equals 1 on this curve, x is 1, the x is either 1 or negative 1. So we have these points. So we're going to go on with this. And the lambda equals 3 case, which I didn't write down here, tells you that the points are 0, 1, and 0, negative 1. Well, we'll go on with this next.